So thank you. So what I have been asked to talk about the supernova and the neutrinos from them. And thanks to Poonam and Shubhendu, we already have reasonable idea about like neutrinos. And this is this neutrino sky. Both of them showed it. So where we would be actually focusing on in this MEV neutrinos, which are very close to the solar neutrinos. So the supernova neutrinos that we are going to discuss today are these MEV ones. Of course, the supernovas, they can create like as a supernova remnant, they can create much higher energy neutrinos somewhere over here, but that's not we are going to focus today. Now, the typical problems in supernova neutrinos can be thought of like basically threefold. The neutrinos are created somehow inside this collapsing core, this core collapse supernovae. And then while they're coming out, they're interacting with the background matter. They are also going to interact with themselves itself if the neutrino densities are too high. So they will have oscillations. So they will propagate. Of course, they will propagate to Earth. And then we had Earth, we have different detectors. And then we want to learn about these neutrinos, their energy spectra, their angular spectra. And also by studying these neutrinos, we also want to learn about possibly about the supernovae as well. Now, the focus of this talk would be mostly on the propagation, but we'll very briefly discuss the production and the detection just to motivate how the propagation of these oscillations can be important for both of this part, the production and the detection. So very quickly, let us go through the production. So it's the kind of supernova that we are discussing are the core collapse events. So these are like of the order of like at least 8 to 10 solar mass. You have this iron core, you have this onion ring like structure from the gravitational collapse. This iron core is collapsing due to its own gravity. And finally, because it reaches the supernuclear density, this is shockwave driven explosion. And at the end, you have this neutrino cooling, and the neutrinos which are coming out of the star are typically of like 10 MeV neutrinos, and this emission time is of the order of 10 seconds. So, but though it's like 10 seconds, they are not like homogeneously over 10 seconds. There are different phases of neutrino emission in this 10 seconds, but that we are not going to discuss today. But let's see how this very nice picture of this core collapse and coming to neutrinos actually doesn't work very well when you go to the simulations. So what has been seen is that this mostly for like stars which are like at least 10 solar mass, this outgoing shock actually loses energy very quickly going through this very dense core, and it stalls, and you have more matter accreting towards them. And the proposal or the solution, one of the solutions which was thought is basically neutrino hitting. So the idea is that neutrinos which are coming from this deep inside the core, while diffusing from the substar, they can dump energy behind this stall shock, and this kind of can create some kind of hydrodynamic instabilities, which was like proposed long back, but like it was very difficult to see these things in even simulations. So, but from last let's say last more than a decade, this has been actually seen pretty well in 2D simulations. Now people have actually reached the idea of like 3D simulations. But in this figure, I mean in this picture, how could neutrino oscillation can come into and actually help us? So now here you see the typical spectra of supernova neutrinos. And as you can see, the supernova can actually produce neutrinos of all flavors, and their average energies are different. So now, if you can somehow oscillate among these different species of neutrinos, what can happen that you can actually have, say, like the fluxes can be different for the more effective neutrinos, like for example nu and nu bar, their fluxes can change. They have many more. They have like their interactions are like different than nu x, and this can in general can change the picture of this neutrino hitting. So this has been like a quite for some time. People are trying to understand if the neutrino oscillations inside the star can actually change or can actually change or can help this supernova explosion. Then comes the detection part. Of course, we can understand while it was the detection part, these neutrino oscillations and their signatures are going to be really important. Now, for the detection part, of course, we should mention that like the last nearby supernova was this 1987A, And as I already mentioned that like most this models of supernova, they predict this neutrinos energy of the order of like MeVs, 10 MeVs, and emission time was of the order of 10 seconds. So these two were already seen. This is like something like we have already tested. And as you know, like there are like plethora of papers just even from this emission time, from the cooling, constraining different kind of physics situations or possibilities. Now, but then the point is, what would happen if tomorrow we have a new supernova? Are we ready for that? So for 1987, we had something like few tens of events. Now, if you go to the present detectors which are running right now are mostly like IceCube and Super Kamioka. There are many other detectors, but these two are the biggest one. As you can say, Super K would be able to see something like 10 to the power 4 events for a galactic supernova, and IceCube could see something like 10 to the power 6 events. And this is something which I like pointed by like Amol and collaborators back in 2000. The IceCube, even it is like it is a very high energy detector. We mostly think of like IceCube for like at least for like say close to PV neutrinos. But then IceCube would be able to see for a galactic supernova. Suddenly there will be a large number of neutrinos coming, so your background would suddenly kind of brighten up. So this was pointed out, and IceCube can actually see very well. Should be able to see for a galactic supernova the light curve, what you call a quote unquote light curve, basically the neutrino time spectra would be able to see. Now, what are the upcoming detectors coming in process? We have the Hyper K, the megaton Water-Cherenkov detector, the Dune, and the Juno in China, which is the large detectors which are coming up, and they should be able to see much larger number of neutrinos compared to what we are able to see in Super K or right now. But here it is important to point out that Hyper K and Juno, these are like they would be looking into the neutrinos through the inverse beta decay. So you would be looking into nu bar and nu bar. So somehow these bars are gone while I change the PowerPoint to PDF, and the Dune would be able to see the electron species. So they have this is complementarity in these two proposals. And it's also important to mention that India is of course part of Dune. You know, like many of our colleagues are there, but recently have started this very small collaboration with Hyper K. Say like now, right now we are like order of 10 people who are like connected into this collaboration, and we look forward for more people to come. So last week in Pune we had this meeting with the KK director and like all other KK members who came, and this is like just a very small collaboration right now, but we will be very happy if others also come and contribute. So now there are now, if you come to the detection part, there are like many different possibilities of many different phenomenological thing can be studied. But I will just point out one thing. This is called the rise time analysis. And here the idea is that like for the very early accretion phase, what happens like for the inverted ordering, the flux rises much faster than the normal ordering. And this we have pointed out much long back, because the idea is the inverted ordering, the flux is mostly consist of the nu x, basically the neutrinos of like heavy lepton, like nu mu bar or nu tau bar. And the normal hierarchy fluxes is mostly dominated by the nu e and basically nu e bar here. And one should be able to see that this is actually rising much faster. This we have actually pointed out for IceCube. But recently for the collaboration, we are also studying for what would happen to a megaton Water-Cherenkov detector. Here you can see we have plotted the cumulative number of events, say like at 100 seconds versus the event rate between like 20 and 100 milliseconds, basically looking at the slope in some way. And as you can see, for like we have looked for like 10 different models of supernova simulations, they show a very large differentiation between the different mass orderings. And now, as you can, I mean, like both these examples are actually to show like how important this oscillation effects are, because this feature we could see because of the oscillations of the supernova neutrinos. Now, what about this propagation or oscillation here? And the oscillation inside the supernovae are very non-trivial, because you have all three flavors are present. And what can happen, these neutrinos while coming out from the center of the core, which is something like we call neutrinosphere, it's like a last scattering surface of the neutrinos coming out of the supernova core. They can actually interact with the electron, and you have this typical MSW oscillation, but they happen pretty far away, some 10 to the power 4, 10 to the power 5 kilometers. But the neutrinos very close to the core can also interact with the other neutrinos, because the density of neutrinos are extremely large close to the core, which is like of the order of say 10 to 100 kilometers. And this interaction gives something which is known as this collective oscillation. What happens because of this large neutrino densities, neutrinos and antineutrinos of different energies, they somehow couple and they collectively change the oscillation, to change their flavor. So this has been pointed out almost, it's like more than like close to be like 2 decades where people are actually studying these collective oscillations. But now recently it has been pointed out that these collective oscillations can be of 2 kinds. So what we used to know as like a typical collective oscillations are now called the slow collective oscillations. So these are basically dominated by the delta m square. And for a typical supernova, this order of this frequency comes out in kilometer inverse, and this happens in few hundred kilometers. But then there is the other kind of oscillation which has also been seen. It's called the fast oscillation. And the idea of this oscillation is that like this is coming from the angular distribution difference of like different flavors, which we'll discuss in more detail soon. But this will happen typically close to the neutrino sphere. And this oscillation, this fast oscillation, is actually driven by completely by the neutrino density, and which is extremely high close to the supernova core, and which can happen in basically in centimeter scale, something like in nanosecond order after they are emitted. So this we have actually pointed out in 2016, and this oscillation, these are like so fast that we coined this word called the fast collective oscillation. And now if we try to understand why is this happening, the idea is that like when the neutrinos are emitting from the core or from the neutrino sphere, as you can see for 3 different flavors, we have shown 3 different lines, and these are say like because their interaction and cross sections are different, so they would be emitted at different times. So for example, this blue is basically this nu mu, nu tau bar, which we call as nu x, they would leave earlier. Now when you are looking into their interaction at some distance, since they have left at different radius, their angular distribution would be different. And this is the main reason where this fast oscillation is coming. And since this oscillation depends only on the neutrino density, very interestingly, this can actually happen even for a vanishing neutrino mass. Of course, that's not the case. I mean, we know that neutrinos are massive, but so these neutrino masses in this kind of oscillation just act as a seed. And this is something very unique in supernova environment. And as I said, like there's like extremely fast conversion in nanosecond scale. Now, if we really try to understand this oscillation in a bit more detail, so the neutrino transport in supernova, as I said, is already pretty non-trivial. The reason you can see is in this Liouville-like equation, the Hamiltonian, apart from this usual kinematic and this MSW term, you have this term which is coming from the neutrino density, and this depends on this density of matrices. So this actually makes this whole problem non-linear. And very interestingly, like this also depends on both the neutrinos and antineutrinos. So what happens, you have a coupled system of neutrinos and antineutrinos, and this coupling can be between different energy and angular modes. And and that's not enough. Like this problem is actually 7-dimensional. What do we mean by 7-dimensional? Because these neutrinos from supernova need not to be like a stationary problem. They are emitted over time. So of course you have to take like, because this evolution is like a partial differential equation. And then on top of that, this slide from Tuhin actually shows it very nicely. So this is the neutrino sphere from the neutrinos are actually being emitted. Now this 3 r theta phi is basically at which direction you want to study the neutrino evolution. You can study it like radially. You can, in principle, you can also study into the perpendicular direction of the emission. And now when neutrinos from say like from 2 different points are actually interacting, so their emission angle and their emission geometry is also important. That gives 3 more variables. So this actually is like one of the most difficult numerical problems you can thought of. But then, for again, Amol and Raphael, they actually proposed this very nice idea long back, like not looking into the nonlinear problem, but rather looking into this linearized problem. What is the idea now? Of course, you can understand in this matrix of densities, the off-diagonal elements, these ones, they actually tell you if there is some kind of flavor mixing or not. So what you do is basically you linearize this problem into the off-diagonal elements. And if you do that, so you get like something like an equation like that. Now what you want to see, whether these off-diagonal elements are growing exponentially or not. If they are growing exponentially, that kind of tells you that I can have like a scenario where I have like some kind of flavor instability. Now this is the driving equation. As you can see, this is like linear into this off-diagonal element, and this omega depends on the energy, lambda depends on this electron densities. But what is very interesting, like this quantity which we call like a spectra. this is nothing but a difference of like fluxes of different neutrinos. And this spectra, which has been actually shown, which we knew from previous studies, that a crossing in the spectra, a zero crossing in the spectra, basically what triggers this kind of flavor instability. So this we can try to understand from this from the example for the fast oscillation. Here, as I explained, from where these angular differences are coming, here you can see the angular spectra of different flavor for a typical supernova simulation. And now if you look into this spectra, what I call basically difference of this angular distribution, that would look typically something like that. Now, it was pretty well understood before that, like, if there is a zero crossing of this spectra, then you could have these flavor instabilities, which indeed has been proven. Like mathematically, it can be actually shown that a crossing of the spectra is a necessary condition and like sufficient one to give this flavor instability. Now, of course, the question is whether this flavor instability will finally grow into a flavor conversion or not. That's a different question. But of course, this would mean like I can have this thing triggering, and this quantity what has been plotted is, you can see, is basically nothing but the difference of these fluxes of neutrinos. And here, like as we were talking about the angular distribution problem, you have integrated over the energy, and this depends on the angle. As this is V is basically your cos theta of this zenith angle. Now, for a typical problem like that, now if you want to convert if you want to look into the probability of conversion, you would find something like that. But what is important, look at the x-axis, that these conversions are happening at a nanosecond time scale. So this can happen only in this extreme dense environment of supernovae. Now, similarly, the slow collective conversion, which we used to discuss, which we knew before, comes when you have the zero crossing in the energy spectra. This also has been like, this was well known, but this angular one is something new. But then the question is, of course, these fast oscillations, we have some understanding how this is happening. But the point is, where are they exactly happening? Now, to probe that, what we need to know? We need to know how these angular spectra are in actual supernova. We can't do that. So we need to look into the supernova simulations. Now, as you know, in supernova simulations, there are many parameters. There are many different groups. They have many different numerical codes which they work on. So here is some kind of a basic understanding. So there is something like this 3D laser simulation from the Garking group, which showed that this kind of crossing can actually happen inside the neutrinosphere itself. And the effect of this kind of crossing in supernova dynamics, we still have not understood well. And then there is this other proposal from this Japanese group where they show these crossings would happen pretty far out. So here is what you are seeing is basically the supernova, this electron density, basically this yellow or the orange curve, and here you see the shock front. And this kind of crossing or this oscillation, what they have seen in their simulation, is happening pretty far out, somewhere very just behind this supernova shock. But in both these two cases, what I have just explained you is this supernova, this kind of fast oscillation or this oscillation of the flavors can happen somewhere close to this shock. And the problem was that how we can actually rejuvenate this stalled shock. So, and of course, we know if there is this oscillation, they can actually help the neutrino hitting. But then, of course, this becomes very interesting for the supernova dynamics. But then the problem is that both these things were studied for an effective two flavors model. So here you actually assume that all the nu mu bar, nu tau, and nu tau bar, their fluxes are exactly same, and which is not a very crude model, because the supernova simulations, they actually showed a behavior like that. But then, of course, this is not, and since we are looking at a new like a nonlinear problem, we actually looked into this problem of looking into fast oscillations, but in the full flavor, in three flavors. And then we found that like one of the very interesting result was that it is not only the ELN, that is not only the difference between nu and nu bar, but rather all other flavors are actually involved. And you not only that this quantity called ELN, but you have to have also these things called mu ln and tau ln. So all these flavors could be important. But then, are they really important for a typical supernova? Indeed, exactly is a very similar time came this muon simulation result, which they actually for the first time. Usually muons are not created because it's considered like the core is not hot enough to create muons. But then Here you can see the results. These black curves basically show the difference of different flavors, but without the muon simulation. But once you plug the muon simulations in, the results are actually shown in this red one. And you can clearly see, especially for nu mu and nu mu bar, there's a large difference of the fluxes which are coming up. So these quantities where people used to consider that nu mu and nu mu bar fluxes are same. So eventually you have like only the G1 and G2, and both of them are same, and the G3 would basically become 0 if you take all these fluxes the same. But the simulations were actually telling that this may not be the exact case. So encouraged by this, we actually looked into this scenario that whether these three flavor effects are actually important or not. So we took some toy examples, and we indeed found very like qualitative and quantitative difference from the two flavor scenario. Now here you can see, like for example, as I already pointed out, the zero crossing of this angular spectra is what triggers this kind of instability. So here you see in this blue dotted line is the angular spectra, but for a two flavor case, and it has actually indeed crossed the zero. And you can see here we are looking at the off diagonal elements growth. They are going in nanoseconds. This is the result. But if you now look into the full problem, that is with all three flavors, as you can see, the spectra is not crossing the zero, and indeed there is no fast conversion. So this whole picture could actually change if you actually include all the flavors. And then there is the other example which is also very interesting. As you can see here, of course, we have crossings in this angular spectra, zero crossing happening in the two flavor, also in the three flavor, but it's happening only in two sectors, that is E mu and E tau. In the mu tau sector, basically when you involve on the muon and tau flavor numbers, there is no crossing. And of course, as you would expect, like in the linear scale, no, where these things are decoupled, there will be no conversion in the mu tau. But the actual problem is nonlinear. So these are the nonlinear results that we studied for the first time, fast conversions with nonlinear in three flavor. And now you can see what would happen for a nonlinear problem. Your off diagonal elements, they are connected. And if one of them is growing exponentially, since all of them are really connected, the ones which did not have any instability to begin with would also grow. For example, here you can see this E mu and E tau, they are growing much faster, and this mu tau is growing slower. It is happening a bit later than the other one, but eventually they will also make this mu tau grow. So this is indeed that this two flavor to three flavor scenario was quite different. But then these studies were actually done. Yeah, so these studies were done actually in time only. But then recently we looked into the problem in both space and time, and here you can see this is the same example. Of course, they are growing at nanoseconds. So here basically the seed of this instability is actually given somewhere here in space, and this inset arms are actually showing the linear result. Now I'm talking when I have both space and time, you have to solve the partial differential equation, and then for the linear case you basically get a dispersion relation. Here you are looking at the Fourier modes of both the time and space, and here you can see that they are actually growing for this E mu and the mu tau case, E mu and the E tau case. But for the mu tau case, the inset is not shown because the linear case actually does not show any growth. But of course, coupled by these two, the mu tau is also growing. Here you can also see so this is basically in color coding. What is shown is this off diagonal elements, and the larger values are showing in darker color. And as you can see, like you will have this very large off diagonal elements grown pretty quickly in nanoseconds. Now, with this, let me very quickly point out. Now, again, the question comes. I showed you two examples, like where are they happening? Now, in this muon simulation, this has been also pointed out that these crossings are happening pretty far away, something like somewhere around 100 kilometers, let's say. So this is basically the shock radius. And in this simulation, the shock is actually failing. It's a failed supernova model. But the crossings, the angular crossings are happening pretty far away. So looking into this, we have started recently, we are looking into this thing that these oscillations can actually happen a bit far away. In certain simulation examples, we are recently looking into this scenario. We're actually trying to probe if a sterile oscillation can actually have any effect on this or not. So in these two scenarios, as you can see, these fast oscillations are happening pretty far away. So now what we are actually trying to look into is like, of course, these steroids cannot take part into this fast oscillation because these are coming from neutron-neutron interaction, and these kind of interactions are not there for active sterile case. But the way the steroids can take part into this by oscillation, but that's the MSW oscillation. So so for a typical sterile problem in supernova, the potential looks like this. As you can see, it's within 100 kilometers, and the potential here you can see like where this omega, basically the delta m square crossing, is happening. Now the interesting thing is, like, as you already know, for MSW1, given a mass ordering, the MSW can happen for either neutrino or anti-neutrino. Now, as you saw, like in the fast oscillation, the driving quantity, this ELN, depends on both nu E and nu E bar. So now, if you can have this MSW oscillation, sterile MSW for say like some EV square mass happening deep inside the star, that has the potential of changing this ELN. And indeed, we looked into this example with the initial ELN, and so there are some more details which I am not covering. Like there is this possibility of a sterile, active sterile oscillation happening very deep inside the star, but it's not really known like how. I mean, the adiabaticity of that potential is not pretty well known. So we have taken certain numbers, but whatever we are taking for all of them, as you can see, this ELN that has zero crossing before is actually lost that zero crossing, and if this sterile MSW resonance is happening before this fast oscillation radius, we can this fast oscillation actually can go into get suppressed. Now the phenomenology of that or how it affects the nucleosynthesis, people have to look in future. So this is something should come up in next few days, this paper, and this is basically which, I mean, yeah, I already mentioned that the possible influence of nucleosynthesis on neutrino spectra, which have to be seen. And with this, let me conclude. So what I actually tried to mention that this neutrino production, that the neutrinos can have roles in the explosion mechanism, and the neutrino propagation in this extreme environment in such supernova are like really very, very interesting and very different from the other oscillation scenarios. And the neutrino detection with the present and the upcoming detector, we should be able to test like supernova models or the simulations, and also would be able to learn about neutrino oscillations. So thank you.
Thank you, Sovan.
So this is regarding this new results that you were showing in the last slide.
Huh.
So are you, if I understand correctly, are you saying that for 1 electron volt square sterile neutrinos, it is possible to suppress fast oscillations completely?
Yes. So, and like, of course, like this is for a certain scenario, like we have 1 octave, 1 sterile, 1 EV square. But the point is, if you, as you already mentioned from in Poonam's slide, so now if you are like really free to go to
next question.
Okay.
The range of sterile neutrino delta m squares you will need, which will suppress fast oscillations completely.
Okay. So again, like what we do not have right now is like this potential I showed is basically from Irene's paper from long back. We have looked into some potential from Mengru and from Taiwan, but they do not have the exact this information, like, because what you need is where this crossing is happening. So what we see, like what we are right now doing is like 1 EV square, but of course the thing is, like, if you actually increase the mass, I mean the mass square difference, you actually go much deeper inside. For example, this, I mean, the Irene and Mengru, they wrote a recently paper on KEV, and there this KEV for a KEV sterile neutrino, this oscillation happening just at the neutrino sphere.
Is it more in decreasing delta m square?
Yes.
Slightly outside.
Yeah, of course. Like, I mean, if the delta m square comes down, then of course it will come down. I mean, it will go a bit outside. But what we really do not know is like the exact detail of this potential, because that would also change from simulation to simulations. And what we get today may change in 5 years. So yeah, so it's like something we should look for.
I have a question. So something you mentioned in the very last, how would this ELN and MSW hamper the standard BBN story? How
Standard BBN story?
The Big Bang nucleosynthesis.
Oh, okay. So there the problem is like probably you won't have this fast oscillation, the ELN thing, because it's a homogeneous one. So you do not have, so these are coming because like your, there's an angular distribution, like when these neutrinos are interacting. But if you have like a homogeneous and isotropic one, there is, so basically it's a linear one. So there, I don't know anyone has looked into fast oscillations in early universe.
more of an academic question because we know neutrinos have delta m square. No? But of course, you mentioned that fast oscillations can take place even when all neutrinos have the same mass.
Yes, in principle, yes.
Right? But then when neutrons have the same mass, it is no, you can always redefine your mass and flavor eigenstates to make them coincide. And then saying that flavor oscillate has no meaning. So how do we?
No, I mean, what I was,
mathematically speaking, what you said is correct, but how do we interpret this?
no, to me, it was like not like neutrinos having same mass, but rather say neutrinos are like massless. So of course, like neutrinos being massless is like also another interpretation of that. But like, I mean, but so what you were saying is like if they have like exactly same mass.
So this is the question. So
Okay.
what do you mean to say that they have to have the same mass, or do you say that their mass square difference could be very, very small, like 10 power minus 100?
Yes, yes, yes.
Maybe that is the right way to.
Yeah, that is
interpret
that
this
that
rather
that
than
is
saying zero.
the. I mean, this was vanishing masses. Rather, I should have said like vanishing mass square difference. Sure, sure. I agree.
Very, very small, though not exactly. zero.
Exactly, exactly. Yeah, yes, yes,
I have a question. If I may.
yes,
As I understand that your fast oscillations are associated with the angular asymmetry.
yes.
Now, if you have an angular asymmetry in the emission, there's always the gravitational waves. They are emitted. Otherwise, you don't have a quadrupole. case.
Okay,
If you have just a spherical emission.
okay.
So have you worked?
No, we have not looked into that. But this angular emissions are like the differences are in neutrinos, and that is coming. Yes.
Energy is going out spherically symmetric way, but the flavors are asymmetric.
Because the cross sections of V and U are.
So for example, like, I mean, okay, if I have that picture quickly. Yeah, okay. So here you see, I mean, this picture is actually from Basu's paper, the reference is here. So here what you see is like, we have actually taken, I mean, for they have what they're saying, since this is happening so close to the star. So this neutrinosphere, even if you think it like a plane, even in that case, it doesn't matter because that what comes is basically from their cross section and their interaction difference when they decouple. So basically the last scattering surface is different. So when you are looking into these neutrinos interacting with far away, they will have some kind of angular asymmetry. So this is probably, this is something. Oh, okay. You are saying he's okay.
Let's thank Sovan. So that's the end of this session. Let's thank all the speakers. And I think we break for tea, coffee now.